Everybody, welcome to this session, and this session will have 3 talks. The first will be on public announcements for non-omniscient agents given by Fernando Velasquez Quesada.
Is it okay, the sound? It feels a little bit strange to have this. Okay, first of all, of course, thanks the organizers for giving me the opportunity to be here with you, and also thanks to all of you for being here on this last day of the ICLA TARC conferences. Okay, so before starting, I guess I would like to give just a quick reason why we have been working in this line. We have been mainly interested in looking for actions that are meaningful not only for the agents, well, not precisely for the agents with which we typically deal with in epistemic logic and in dynamic epistemic logic. We have been interested in thinking of agents that do not have all these ideal properties, and then try to find which ones are the actions that are meaningful for them. Well, as Hans already talked during TARC, we have been trying to do some work in representing changes in awareness. We have been doing also some work representing inferences for this kind of agents. And, well, of course, once that we start to deal with different kind of agents, then it also makes sense to look back at the actions that we have already studied in dynamic epistemic logic and take a look to see how these actions affect the knowledge of these new kind of agents. Okay, so the idea behind public announcement logic, I guess, is, well, I guess most of you know it already, but the idea is pretty much simple. We are simply representing, which I think is the simplest way of communication between agents. You have someone, possibly God, telling everybody something is the case, and since the announcement is public, that means that everybody realizes the announcement, but everybody realizes that everybody is paying attention to the announcement, and so on. And something nice about this action is that it has a really simple representation in Kripke model, which is a standard semantic model for epistemic logic. The only thing that we need to do is to get rid of those words in which the announced formula is false. And that gives us immediately, or that represents directly, the effect of this kind of announcement over those particular kind of omniscient agents. And also public announcement logic provides us not only with this, the idea of the operation and the semantic definition of how the operation, how the action affects the knowledge, but also with modalities that allows us to build formulas, and then we can state within a formula, this is the way in which an announcement changes the knowledge, the belief, whatever we want to deal with, of the agent that we are dealing with. But as we all know, there are a lot of idealizations that we do when we are working in epistemic logic, in particular when we are working with the standard possible word semantics. And, well, here are some of those idealizations. Those agents are typically thought of being aware of everything that is involved in the situation, meaning they are aware of every single atom, they have every single concept of the language in their minds, and as a consequence of that, they are aware of every single formula within the language. The knowledge of these agents is closed under modus ponens. This is just the typical K axiom. They know every single validity. We have the, as stated in the necessitation rule. And also, when we move to the dynamic setting, we also make some idealizations about these agents. For example, after a public announcement, the agents not only get the formula that is being announced, they also get every formula that is logically equivalent to the announced formula. They get also every formula that is a logical consequence of the formula that has been announced. They also get every logical consequence of the announced formula plus the information that they had before. And also they are supposed to have perfect memory, meaning that if something was announced, then they will not consider those possibilities anymore. And then, well, one way of looking at public announcement logic in this setting is to say, well, we are only looking at the way in which a public announcement affects the information of some very particular kind of agents, meaning the agents that have all these ideal properties. What we want to do is simply more or less the same idea, but then look at some different kind of agents. We are interested in agents that are not such powerful reasoning, so to speak. And of course, in particular, well, not of course, in particular, we are interested in one kind of agents. We are thinking about agents that are aware of every single possible formula, meaning the lack of omniscience, so to speak, is not given because they are not aware of some concept. The problem for these agents, quotation marks, is that the knowledge that they have doesn't need to be closed under logical consequence. What I mean is that they may know P and P implies Q without knowing that Q is the case. And also they might not know every single validity. Maybe here's a good way of, here's a good moment to try to to emphasize the difference between the agents that we have in mind and the agents that lack of awareness. Put it in some dynamic way, the agents that lack of awareness, the only thing that they need is to become aware of some concept, and under some definitions of awareness, they will become then logically omniscient. The agents that we have in mind are those agents that lack of inference, meaning that they haven't done every single inference step that they can perform, and therefore there are still some formulas that are true, but they haven't realized that they are the case, that they are actually the case. Okay, so the first step, of course, is then define a framework in which we can represent these kind of agents. Technically, the framework that we're going to use is exactly the frame of awareness logic. We're going to change only a little bit or understand a little bit different the extra stuff that awareness logic gives to us. So from the point of view of the language, we have the standard epistemic language, we have the universal modality over there, and what we have also is this operator A that allows us to build formulas of the form A5. Semantically, we still have the same tricky model, meaning we have a collection of an empty collection of possible worlds. We have an indistinguishability relation, which we're going to think of it as an equivalent relation. We still have the valuation, and the extra stuff that we pick from awareness logic is that now we have a function that is telling us, or that is returning us a set of formulas for each one of the possible worlds. Now, in awareness logic, this is understood as the formulas the agent is aware in each one of these particular points. Here we're going to understand it in a different way. Our intuition is that each one of the points, each one of the worlds in the model is actually, or can be seen syntactically as a maximal consistent set of formulas, right? Exactly all those formulas that are true in that particular point. And well, our agent, even if he's aware of every single concept, he still may not have realized that every single formula, each one of these infinite formulas is true in that particular point. So we're going to think that this function A, that's a pointer, this function A is just telling us those are the formulas that the agent actually knows for sure, that the agent has realized, that the agent has acknowledged that they are the case. Semantic interpretation is, as usual, the box modality is as in epistemic logic. For giving meaning to formulas of the form A phi, we're going to say that that formula is true at a point W if and only if the formula phi is in the set of formulas that is assigned to the world W.
Can you be aware of the false formula?
Yes. We don't have any restriction about the formulas that are going to be in this set. You can put any single formula in there. Yes, that's the case. And well, that's a piece of notation. We're going to use the double brackets to indicate, to represent all those worlds in the model M in which the formula phi is the case. Now, the next step is to define the concepts that we're going to deal with, which are, as you might expect, the concept of implicit knowledge and explicit knowledge. For the concept of implicit knowledge, we use just the standard approach, meaning that we're going to say that an agent knows implicitly some formula phi, exactly in the case in which this phi is true in every epistemic possibility that the agent can see. So that's the definition that we have here. Now, for the case of explicit knowledge, this is going to be a little bit different from the standard definition that it's used in awareness logic, because as I was mentioning before, our idea is that the agent can only see a restricted part of the formulas that are true in each one of these points. So in order to say that the agent knows explicitly some formula phi, we're going to ask for the agent to see only epistemically possible worlds in which the formula is true, and moreover, the agent has recognized that the formula is true in those points. Well, as you can see, this formula, this definition is slightly different of the standard definition of explicit knowledge in awareness logic, because now we have the A operator inside the scope of the box. And well, we can also define the possibilities, meaning implicit possibility and explicit possibility. Implicit possibility is just the diamond, as it's usually done. And for the case of explicit possibility, where again we follow our intuition, that means that for the agent to consider explicitly some formula phi, what we need is for him to see a world in which phi is true, and moreover, she has realized that that formula is the case in that particular point. And a piece of notation again, this formula at the very bottom, phi and a phi, what it's telling us is this is a point, is identifying, characterizing those points in which the agent recognizes that phi is the case. And we will abbreviate those formulas in this form. Okay, so now we have the representations of the agents. In previous works, we have proposed two straightforward definitions of a public announcement for this kind of agents. And of course, the most immediate one is just to take the public announcement definition in standard public announcement logic and then put it here. And this is exactly this called implicit public announcement. We have a model, we have a formula, and which one is going to be the new model, the model that we get after this formula is announced publicly? Well, what we're going to do is get rid of all the words in which the announced formula is false. The accessibility relation is restricted to the new domain. Evaluation is going to stay the same. And the set of formulas of each one of the points is going to stay the same. And we introduce, well, it's introduced as it's typically done. There is a modality that is allowing us to describe the effect of this action. We say that at some point W, phi is going to be the case after an implicit announcement of chi, exactly if chi can be announced. And after the operation, we have phi. So this is just typical stuff. Now, what's the defect of this action? Well, and even before going there, I think it's a little bit easier, and maybe for the sake of this presentation, just to think of formulas whose truth value is not changed by the operation. We know that in general, an announcement can change the truth value of a formula in the case in which the announced formula involves some epistemic modality. But just for understanding what's the effect of these actions, we're going to consider that we are dealing only with formulas whose truth value doesn't change after the operation. So what's the effect of this action that we just defined? First, for implicit knowledge, after this implicit announcement of a formula chi, the agent will always have implicit knowledge about the formula. Why is it the case? Well, because after the operation, we only have worlds in which chi is true or chi was true in the original model, but then we are assuming that the operation doesn't change the truth value of the formula. Therefore, chi is going to be the case in all the worlds in the new model. And how does this operation affect an agent explicit knowledge? Well, the action doesn't guarantee that the agent is going to have explicit knowledge about the announced formula, because even if we're going to have only chi worlds, only worlds in which chi is the case, the agent may not have realized that chi is the case in each one of these points. If we have that, meaning if we have this condition, then we will get, or the agent will get explicit knowledge about the announced formula. And then, of course, there is another small variation of this implicit public announcement, what we call an explicit public announcement. The definition of the operation is almost the same, meaning that we still get rid of all the points in which the announcement is false. And what we're going to do here now is just to add the announced formula to each one of the sets of formulas, to the set of formulas of each one of the worlds. This is then stating somehow that the announcement is explicit, so every agent realizes, or in this case, our agent realizes that the formula has to be the case. Syntactically, we introduce, again, another modality with a standard semantic interpretation. And then, again, what's the effect of this action on the agent's knowledge? Well, again, since we're getting rid of every point in which the announced formula is false, then this announcement guarantees that the agent is going to have implicit knowledge about the announced formula. But moreover, since now the agent is recognizing, is acknowledging that the announcement is true, then the agent will have explicit knowledge about the announced formula after this announcement that we just defined. Okay, so everything seems to be working really nice, and we have nice properties that seems to fulfill our intuition. And still, one of our friends, a colleague, made us a nice observation, in the sense that, well, are these definitions proper for the kind of agents that we have in mind? Because basically the only thing that we did was to take the definition of a public announcement, then modify it a little bit in the case of the explicit public announcement, but that's it. Well, something that the previous public announcement do is that they get rid of every single point in which the announced formula is false. But that's precisely the opposite of what I was discussing at the very beginning. That's precisely the opposite of the intuition behind the agents that we have. Because as I was saying before, an agent may not realize that some formula is true or false in some particular point. So even if the agent considers only possible a single world, and even if he has a formula, she has a formula, she may not be able to tell whether the formula is true or false at that particular point. So it's not reasonable to assume that after an announcement of some formula chi, the agent can safely remove every single point in which chi is false, because simply she may not have realized that that formula is false in one of these points. What can we do about that? Well, there are for sure some points that we know the agent can eliminate safely, and those are precisely those points in which chi is false, and moreover the agent has recognized that the formula is false. And this is exactly the idea behind this definition. As we see, what we are changing is the set of points that are going to be discarded. Instead of removing all the points in which the announced formula is false, we are only going to remove all those points that the agent has recognized as not satisfying the announced formula. Remember that this AG on the top means that the formula that we have here is not phi and A not chi, sorry. And with respect of the set of formulas, we're going to keep them exactly the same. We introduce some modality for this operation. And then now, to analyze which ones are the effects of this action over the knowledge of our agent. Well, now this action doesn't guarantee that the agent is going to know even implicitly the announced formula. Why? Well, because even if she's going to discard all those possibilities, all those problematic words that she has recognized, she might not get rid of all of them, meaning that after the operation, there might be still some words in which chi was true hanging around. And of course, if the operation doesn't give the agent implicit knowledge about the formula, then it's not give also the agent explicit knowledge about the formula, not only because there may be still some not chi words hanging around, but also because even if the agent can manage to get rid of all of them, that doesn't guarantee that the agent has recognized that the announced formula is true in each one of the remaining ones. So one could then wonder, what's the effect of this action? Apparently it doesn't do anything that is useful for the agent. But indeed it does something. What it does is to allow the agent to get rid of all explicit possibilities in which the announcement is false. Right? Among the surviving words, there will be none of them will be a word that the agent identifies as satisfying the negation of the announcement. So apparently this definition solves, well, this definition I think solves more or less our intuition, meaning that we are now eliminating those words that should be eliminated and no more. But still, what is going to happen with these problematic words that are going to survive this operation? Because also intuitively, one could think that a public announcement should allow any agent to get rid of every problematic word. And our answer to this kind of tension between these two ideas is that both of them are correct. The only difference is that we need to take care of when each one of these points, each one of these problematic points can be eliminated. We know that some of them will be eliminated immediately after the announcement, exactly those that have been identified as problematic words. There will be still some of them that will survive the announcement, but still they can be eliminated as soon as they are identified as problematic if the agent remembers the announcement that just took place. And for that, it's just a very simple variation. Again, we're going to keep this as the set of words that are going to be discarded. Again, we're going to just remove those words that the agent identifies as being problematic. But then what we're going to do is to force the agent to remember that the announcement has taken place, meaning we're going to put this formula in each one of the sets, in the set of formulas of each one of the words. Again, we introduce some modality. And now, what's the effect of this action? Well, still, it doesn't give the agent implicit knowledge of the announced formula, again, because some problematic word may survive the operation. And of course, it doesn't give the agent explicit knowledge about the announced formula. But now, instead of needing two things, instead of needing for the agent to recognize problematic words and unproblematic words, we only ask for the agent to recognize problematic words in order to get explicit knowledge. We still have this property that's telling us that the operation allows the agent to get rid of every explicit possibility in which the formula, the announced formula, is false. But now we also have that after the operation, in every single possibility, in every epistemic possibility for the agent, she will have acknowledged that the formula, the announced formula, has to be the case. And then what can the agent do? Well, simply as soon as she realizes that there are some words that have this conflicting information, then she only needs to get rid of them. There's a typo here. This one we should get rid of this union and something. That should be just preserving the same collection of formulas as in the original model. And the key part is that these are precisely the words that we're going to get rid of now. So every time that the agent wants to perform some depuration, the only thing that he needs to do is to look at each one of the points and to see if she has conflicting information about that point, then she can safely get rid of it. We introduce some modality for that. And now we can tell the full story of how a public announcement affects the information of our kind of agents. So first, we have the last definition of a public announcement, the attentive public announcement, which allows the agent to get rid of every problematic word that she has identified. Of course, that doesn't guarantee that she will get rid of all of them, because, again, if she hasn't recognized some point as problematic, then she cannot get rid of it safely. But still, we know that she will remember later that the announcement has taken place, meaning that all the surviving points should satisfy the announcement. And then what we get is that as soon as she managed to identify all those problematic words as problematic, then she will be able to perform this depuration. And finally, she will reach a point in which she will know the announced formula explicitly. So again, we think that this is a nice way of describing the effect, because, well, being a non-omniscient agent is going to take her a little bit more of time to reach the conclusion that any omniscient agent will get in one single step, but still there is a way for her to do it. Okay, so just summarizing. What we have done is, well, probably the first steps only to deal with public announcement for some particular kind of agents. Again, for those kind of agents in which the problem, like in quotation, is that they don't have, their knowledge is not closed on their logical consequence. And what we have done is discuss the actions, which one should be the proper actions representing how a public announcement affects the information of these agents. We have provided model operations and modalities for this. And also in the proceedings, you will find the action systems. And we have discussed which one is the effect of these actions in our agents. Further extensions. We have been working only from the perspective of a single agent. And even if the move from a single to a multi-agent case in epistemic logic, in public announcement logic at least, is straightforward. We just add the index. In our case, there may be a little bit, there may be a tricky points, because now, even if the announcement is public, each agent may not be completely sure of how is the announcement affect the knowledge of the other non-omniscient agents. So there is uncertainty to take into account here. And of course, this is just one particular kind of agent. So we will be also interested in studying how these kind of actions, public announcements, affect the information of other kind of agents. Okay, that's it. Thanks a lot.
When I make an announcement of something that you are not aware of, so I use a proposition that is not in your awareness set, wouldn't you immediately become aware of it because of the announcement?
Yeah, well, I would say so. As I was saying, we're assuming that these agents are aware of everything. But indeed, if we were thinking about agents that are not aware of every single notion, then I would say that hearing an announcement of something that I'm not aware of will make me immediately aware of that situation.
Yes.
And then in that way, I guess that if we are thinking again of those agents, then the operations that we have here, or the operation should be slightly different of the ones that we have here.
But it can be phrased in terms of your operations.
Yeah.
Okay.
Yeah.
Yes. Right.
Any other question?
Well, I have a somewhat similar question because I find that you describe very fascinating variations of interactions of awareness and knowledge. And well, the way I understood it, the other agent making you aware of something, in this particular case, you model is as the outside observer playing that role, right?
Yeah.
But, well, to come to my question, in the multi-agent setting, one thing you could maybe consider is that as here you have different sorts of announcements, these could somehow determine different agent types of how agents react to new information. And so I'm wondering if that occurred to you. And well, a somewhat related question in the multi-agent setting is that if you have several agents, you could have some by communication, you could reach a communicative core of the things that the agents are distributedly aware of, so to speak, and the maximum of information they can reach by communication given their current state of awareness. So, well, have you some thoughts on these matters? Yeah.
Okay. Actually, I haven't tried to explore the multi-agent case. I have the feeling that should be a little bit more complicated, of course. For example, just as I was mentioning, now that we still may have uncertainty because even if the announcement is public, I may not know how it's going to affect each one of the different kind of agents that may be involved. That's one of the points. And I guess that's as far as I have thought about this kind of things. I haven't explored too many things. But
would you imagine agents to reach a stable point by communication, given their state of uncertainty and awareness?
Yeah, I mean, of course, it depends on which kind of actions giving communication you allow, right? If it's announcement, which, as Jan was saying, implies changing awareness at some point.
No, any kind of dynamics, so any kind of action models.
I mean, I think that would be actually a nice way of describing well, conversation or these kind of things, right? That we make an announcement, we try to agree on some definitions, some of them perform some inference, some of them perform the other. But yeah, I guess that should be able to represent, like, there should be a fixed point of everything that we can get to know via this collection of actions, given the information that this set of agents has at the very beginning.
So there will be some sort of distributed knowledge
reachable under some collection of actions. But
Okay.
Yeah.
So one last question.
I was just curious about your choice of taking things that you're aware of to be sentences rather than propositions. So you know propositions, but you're aware of sentences, and there might be some propositions that you can't be aware of because there's more propositions than there are sentences that could express them. And you might think that if you know a proposition, not only do you have to be aware of it if you know it explicitly, but you have to be aware of the fact that that sentence expresses a proposition that you know. So why did you go with being aware of sentences rather than propositions?
Could you rephrase it a little bit more again? Because I don't see too much of a difference between, if by propositions you mean exactly just what, plain formulas in the language?
Subsets of W.
Subset W,
yeah.
Okay.
So take A to be a function into the power set of W instead of the power set of L.
Okay.
Right, because some propositions won't be expressed in models, even if they're finite, right?
Sort of linguistic unawareness, that I don't know some particular proposition P or whatever. But the other is that also logical unawareness here, right? I mean, I don't know that P and Q implies P or Q and P or whatever, right? Now, To me, if I'm announcing some complicated logical formula, but I don't know logic, I understand the earlier thing was all about information, right? I want to make people aware of some proposition.
Yeah.
But shouldn't I know the logical structure? Like for instance, I might be non-omniscient, but I might know the scheme that alpha and alpha implies beta gives me beta, but not know this for a particular fact, right? I may not be able to combine it. So I don't know how these sort of syntactic approaches would be able to get there.
You mean to
Do
be
you
able to deal
understand
with schemes properly?
Yeah, I'm just wondering if there is some way of doing this.
Any other questions?
Yes. So what happens if you take, as you suggested it in your future work, a semantics which is purely semantic in a sense, like the semantics of Meyer and Burkhardt that was presented at the first talk of talk. In that case, if you define this public announcement operator directly, purely semantically, wouldn't you obtain maybe a canonical way to define public announcement, which is maybe more natural in that sense?
Well, I think that if we work in a purely semantic setting, we will still have at least some closure on the, I would say, on the logical equivalence at least. And well, one of the reasons why we have chosen to work with formulas here is just because we want to avoid any assumption about the reasoning abilities of the agents. Now going into a more semantic setting, something that I have tried a little bit is to work with neighborhood models. And I think for that there is already a work of Johan van Bentem and Erin Paquet in which they deal with the notion of evidence, but within that discussion they say something about how public announcement affect the knowledge of these particular agents. And still something that I like, or some reason why I prefer to work with formulas, at least in this case, is that you don't get any closure property. Meaning you just have the formulas in there, you don't get anything else beside that. If you work in a little bit in a more semantic approach, then you will get, I think, at least closure on the logical equivalence, which may be too much in some cases. But still, that's one possibility, I guess.
Okay, let's thank the speaker once again. So the next, we have two more talks for this session, both on subspace logic and announcements, and by different authors, but both will be given, both the talks will be given by Hans.
As I'm giving two talks, I have been given the use of two hats that I will wear with the two different talks. But even apart from that, as I want to give these two talks that are about the same topic, as I want to present them in perspective, I'll start without a hat. And that will be when no, lights up, please. Well, I suppose the lights will come up anyway. Therefore, I will start by a small example. Could I have the lights up, please? Yeah. It takes some time. Okay. So this will be a talk that is about subset space logic and about public announcement logic. So we have subset space logic. And we have seen various, could you have the lights up, please? Yeah. And we have public announcement logic. And let me present this by a very simple example that will demonstrate the setting of these different logics. So take the very typical case of uncertainty between P and not P. And we do this on the left and on the right-hand side. So both these logics have a language where we have modal operators for knowledge, but also, well, what you could call, well, the standard necessity or possibility operators for something other than knowledge. So here, well, there is uncertainty about P, so the agent doesn't know P. Okay. But in subset space logic, truth is determined relative not just to a point, but to a point and a subset of the entire space. So you might say that is true relative to this point. Well, it's actually a world, but I just called the world P, and the subset of the entire space. Now there's a smaller subset, the one that just contains P, and relative to that subset, P is the only alternative, so there P is known. So from the perspective of this point, you could say that P is true, and in fact, well, implication for some other reason, there is another subset, such that in the restriction to that subset, P is known. And that subset is the one that consists just of P and not the one of P and not P as well. And where this, well, this is the standard epistemic modal operator, and this is what you could call the diamond, a more general modal operator, which stands for effort. So you might say that, well, if P is true, then after some effort, P is known. Okay, now we move to public announcement logic. And here the perspective is not a pair of a state and a subset, but just the state. So here as well we have that P is true, but P is not known. Okay. Now what do we do in public announcement logic? Well, you can also make some sort of distinction between the P and the not P states. Namely, you can announce P. And then you get this part of the model where P is true. Therefore, P is known here. Therefore, at this stage, you can say that P is true, well, and or implies for other reasons, and I can make an announcement of this to the agent who is uncertain about this, and then the agent knows P. Okay, there's yet another setting of this public announcement logic where you take this as one of a set of possible announcements, and then we have a same shape of formula that says that we have P implies diamond KP. Oh, that's what we had on the left-hand side as well. But the difference here is that here we go to another structure, whereas here you might say, well, it doesn't appear from this example, but here we actually go to a different subset in the same structure, and the evaluation of what happens after the diamond is yet back again in the original structure. Whereas in public announcement logic, you indeed go to a different structure. Okay, well, this is almost the general introduction. Now, before I finish this general introduction, this in itself is an original shape of formula. If you look at this in a setting where we do not just have operators K and diamond and box, but this is a bit too, there's too much echo. Maybe I should talk less loud. There's another logical modal setting wherein this is a familiar shape of formula, because that is saying so much as that when phi is true, then you can do something such that you know phi, which is known as a formalization of the knowability a la Fitch. So this is a setting of a formula shape that has sense in a setting of a knowability logic, yet another modal logic. But here instead, this shape describes a property of subset space logic of open sets, and in this logic of announcements with, quantifying over announcement, it yet defines another property. Okay. One other thing I should definitely mention in this setting. So this subset space logic is better known, or maybe not better known, alternatively known as topologic by Larry Moss and Rohit Parikh. And actually this public announcement logic has also a strong Rohit Parikh link, because this is by Jan Platzer, a student of Rohit Parikh and Melvin Fitting. So, and these logics came around in about the 1990s, well, or before or after, and have since independently developed. And what I'm presenting is a number of ways to bring these two logics together, but both from the perspective of my work with Philippe Balbiani and Andrei Kurinov in Moscow, and by the work of Yi Wang, who was going to present this paper, and Thomas Agopoulos. And that's a different way to combine this public announcement logic and subset space logic by way of a slightly different version of the semantic. Yeah, but the unifying pattern is to bring these two different approaches together. Okay, so this is the time now to put on one of my hats and proceed with the transparency of the first of these two presentations. Okay, one hat. Now I open the first presentation. And here I go. Thank you. Okay, so I'm the Hans van Dippenaars person, and Philippe Barbiani and Andrei Kudinov are not here. So in this case, and I will be a bit schematic also, I've been instructed, and an instruction I should clearly follow, to condense these two presentations to somewhat less time so that we have more time for lunch, given the heavy program in the afternoon. So one thing we did with the subspace logic is that we considered a somewhat weaker version of this logic that we call weak subspace logic. And the reason for doing that is that if you combine this subset space logic with public announcements and you take the standard version of subset space logic, you get into difficulties with what is known as the cross axiom. And the cross axiom is describing some interaction between the modal diamond and the K operator. So, and the overview of what we have done is that first, we provide the completeness proof of this weaker subset space logic, the WSSL. Well, have a complete axiomatization and do a complexity result. In fact, it is p-space complete. Then we add this subset, we add announcements to this subset space logic, axiomatize that logic, observe actually that its complexity does not increase by applying a technique by Carsten Lutz, sometime presented at AMAS. And then third, we have a subset space logic with arbitrary announcements. And the arbitrary announcements is the quantifying over announcements, as in my initial example at the beginning. And that actually makes a difference for the logic, because then the logic is more expressive and is likely to be undecidable, although the actual paper doesn't give the undecidability proof. So the language is the one with the K and the box as here, as in the example. The typical structures for subset spaces have, I'll do this a bit schematically, given a domain, you define a set of subsets of that domain. Then you define a number of pairs of points and subsets, so that you have a collection of pair subset pairs indeed that defines the topology over which you reason. And then to interpret the K and the box operator, you define an accessibility relation relative to the K operator, which says that if you have an XU, then you can have a YV accessible from the knowledge perspective, as long as X and Y are both in that set. Well, if the U and V are the same set and X and Y are in that set. Whereas the effort accessibility relation is such that XU, from XU you can get to YV as long as U is a superset of V, and the point is the same. So you either shift the point, then you can interpret the knowledge, or you shift the subset, and then you can make a sense of effort. And so using that semantics, we have that indeed, you know proposition phi if for all other points that you can access in that subset U from X, phi is indeed the case. Whereas after any sort of effort, phi is if for all subsets of that U, you also have that phi. Okay. Now the weak aspect is that you have some issues. If you have a certain subset, for example, the subset V here, if you have another subset U that contains V, And you have two pair subset combinations for the smaller set V, but not all of those are used, so to speak, are permitted for the larger subset U. Here again, I wish not to present that example in detail, but if you want to have an interaction axiom that says that after some effort, and the head K is a diamond version of the K, so after some effort, you consider it possible that P, that it should apply that originally you could already consider it possible that after some effort P, that is false if if a certain property is indeed not satisfied for the pair subset relations. And this property that should be satisfied is that if you have a smaller subset that contains some points, such as the pair subset combination is allowed, then it should also be allowed for a larger subset containing that particular subset. So anyway, this is an interaction axiom that we did not require to be valid to get axiomatization of this logic. Here is then the axiomatization, which is the expected axiomatization of this subset space logic, according already to the classical Mosparic version, minus the cross axiom. Again, I do not wish to go along all these axioms, but let me point out that the modality has the typical aspects of an S4-like modality where you can have smaller subsets and then it remains a subset, so it has some transitivity aspects, and the K modality has the properties of knowledge. As a result, this is therefore then also a standard result that this is a complete axiomatization. As the particular novel result of this paper is that this complexity is p-space complete. Here, you might say this is a technical contribution and effort achieved by Andrei Kudinov, who is by doing some not number crunching, but formally crunching, achieved this result. I will not explain here why in this particular case it is p-space, but I can easily explain why it remains p-space if you go to a more expressive logic. Okay, here we get to the part that is of more interest for this audience, wherein we are going to combine subset space logic with public announcement logic. And you might say, and the semantics of this operator is the crucial aspect where I wish to catch your attention that is different from the previously known work on this area. So given to the language we already had with the K in the box, we now add the after phi psi. So after announcing phi psi. And what would you expect? In public announcement logic, an announcement of phi means that you, restrict your model to the phi states. But that is for a semantics where indeed the observation point of evaluation are states, but not state subset pairs. Now we have to do some public announcement-like thing for structures where the units of evaluation are point subset pairs. So what is the solution here? Well, in such a pair, XW, after phi psi is true, first, the to be expected thing for public announcement, first phi should be true in the current point XW, in the current pair. And on that condition, so that's you might say the truthful condition of truthful public announcements, then in the consequent, you are going to rebuild the model somehow, but not, of course, as in public announcements, but slightly different. So how is that different? Well, instead of the F, which is our current subset space structure, which, I wasn't too particular about that detail, my apologies. So that would be a triple, X as W, where W is the essential collection of point subsets. You leave the first two parameters the same, but you change the number of pairs in this collection W, and you call this a W, relative to the announced formula phi. That in this changed model, given the truth of phi, then the post condition psi should be holding. and this changed model is defined as the number of YV, V, such that satisfy phi. So in a way, it's obvious. So the restriction is not to the phi states, but the restriction is to the phi pairs, YV. This is one choice. In the other talk, I will present another choice to define the semantics, which is slightly different, also because the other authors had some different additional restrictions on the subset space here. Given that semantics, then the rest unwinds automatically using the techniques of public announcements. Therefore, this part I will not explain in detail. So if you have this public announcement logic, you have a number of axioms that are known as reduction axioms because they are all equivalencies that relate the post condition of an announcement to a formula wherein this announcement is pushed a bit deeper into the formula. So the top one says that after announcing phi p for variable if and only if phi implies p. However, this elimination of the announcement from a formula is not always that easy. I will not explain here why it is not always that easy. Therefore, we need to have other conditions to eliminate that announcement. For example, after phi not psi for the negation, well, if and only if phi implies not after phi psi. Or, for example, after phi disjunction, if and only if each of the disjuncts holds after phi. So doing this for every logical operation that can follow an announcement in our language, we have all these reduction axioms, and that is already almost a demonstration of the completeness of this addition of public announcement to subset space logic, because these axioms together show that you can push, if you have an announcement, you can push it deeper into a formula until you reach an atomic variable p somewhere, and then you can eliminate it, because after phi p is equivalent to phi implies p. So therefore, any formula, in this subset space logic with announcements that contains an announcement, you can eliminate that announcement, and then you're back to the subset space logic that you already had, bingo. So it's a complete axiomatization. Also, the complexity here is easily determined because of a technique pioneered by Karsten Lutz in a well-known AMAS paper. This complexity doesn't seem, at least on first sight, trivial, because in some of these reduction actions, like the one for disjunction or the one for negation, if you have this announcement phi on the left-hand side, on the right-hand side you have it twice. So this seems to blow up, right? But there's a technique where you replace each of these announcements by a propositional variable, a new propositional variable. You have an equivalence of that variable to that formula on the side, and then you continue the reduction relative to that variable, and, it doesn't matter to blow up that variable. Therefore, there's some kind of polynomial polynomial time reduction that you can make to, in this rewriting business, such that the complexity doesn't become higher than the p-space you already had. It's just p-space plus polynomial is still p-space. Okay. And I think I must, so if I now run out of time, this is to the great disadvantage of my, not my co-authors, but of the other paper, right, who will kill me if I spend all time on my own paper. So I should really speed up. So I should have sufficient time to wear my other hat. Just before I move to the other hat, so there was one other addition that I promised here, which is subset space logic with arbitrary announcements. The initial example I gave was actually also the example that motivated me to look into relations between these logics. Yeah? And the initial example had indeed a diamond that could be interpreted for there is an announcement after which. Yeah? So now here, instead of that diamond to distinguish the effort diamond from the public announcement, quantifying diamond, we write that as with an exclamation mark, a bang in between the square brackets of the necessity-like operator. And then we have that the semantics of after any announcement phi, this is read as after any announcement phi, is that you can replace this by the announcement of, well, a particular operator, any particular formula, on condition that that formula doesn't contain these exclamation marks for certain technical reasons. And then after any announcement phi is true, if and after if and only if given a formula phi that doesn't contain exclamation marks, on condition of the truth of that formula, in the restriction of the model to that formula, the postcondition phi should then be is true. Remark on a method of, you might say, more in speculation. Because given that we have a diamond that stands for there is some effort after which phi, where effort means going to a reduced to a subset of a given set, and given that we now have another modality which stands for there is an announcement after which some phi, where that means for a subset restriction after which that phi, what's the relation between these two operators? Wouldn't you prefer to have a single one? We struggled, well, we didn't struggle, but what we did is we simply had both and looked at the technical implications of combining both, but there is still the open question of what the relation is between one and the other. Because, so the question is, given that we have diamond phi, and the diamond relative to the announcement phi, given that we have phi is true after some effort and phi is true after some announcement, what should be the difference between these two logical operations? Well, two suggestions here. The first suggestion is that the true after some effort operation has more the flavor of conditional reasoning. Why is that? Well, in the logic of in subset space logic, the diamond means that there is, well, maybe a smaller subset relative to your current point of view in which you can make something true. But that something should then be evaluated in the original model, because that something can be, again, a modal formula. Well, this is conditional to a smaller subset is something true in the current model. Whereas public announcement logic, the main intuitive, you might say, advantage point of that logic over known logic such as conditional logics is that you shift your perspective to another model. So is there an announcement after which something is true? Is there an other model completely changing our perspective such that something is true? So it's a difference between conditional reasoning and you might say, well, PDL-like consequences of action reasoning. Well, the other intuitive reason is that there might be well, given that we have these two different operators, and given that dynamic epistemic logics, such as public announcement logics, are, well, observer viewpoint logics that have no, well, active agency form of operator. It's also always difficult to model agency in that setting. That the subset space operator in the context of this dynamic epistemic logic has more the flavor of an agency related operator and might have some uses there. Well, enough on these well, considerations on the interpretation of this logic. Then I should continue the pace of this presentation. You can show that this logic is more expressive by using techniques from arbitrary public announcement logic. I will not go into that. You can axiomatize it, it's complete, and it's conjectured to be undecidable for similar reasons as the undecidability of arbitrary public announcement logic, a result obtained by Tim French and myself at some stage. Yeah. Okay, that's one hat, and now I'm going to close this one and open the other and take off this hat. How much time do I have left?
Can we make comments in between?
Comment? Well, yes, you can make comments in between. In between or at the end, whatever.
Well, I prefer now to self.
Yeah.
So I have two unrelated comments.
Mm-hmm.
The first one is a technical one. So this renaming technique that you mentioned does not originate from the work of Hans and Lutz, but it's being used extensively in logic before that. And to reduce first order formulae down to some sort of normal form by
Ah.
systematically reducing new predicates and
Yeah.
renaming and thus reducing the quantifier time.
Okay, thank you.
It has a longer rich history.
Thank you very much. Yes. So Pastor Lutz's result is more applying that technique in the setting of public announcement logic.
Yes.
Yeah.
He may make references to this or to, I mean, I know many more sources where
Oh.
it has been used. I've also used it, but I certainly learned this from James.
Thank you.
And so the second is regarding your, actually the question and the suggestions that you made about the how to interpret and how to put together the logic. So I suggest slightly different view on this effort that you call, namely learning over time. That is, think of it kind of a branching task structure that evolves. So at a given moment of time, the agent knows something, but it has incomplete information. But let's say he learns over time, and this learning you present by possible shrinkings of his information set.
Yeah.
See, and so that in over time he will come to a point where he knows more, and so that his information set has shrunk. So that if you think of these dynamic operators as he will know in the future, then basically it gives you the idea of instead of thinking of an effort, learning. But he can also learn by hearing a public announcement. So that's again learning, but it just comes from external source. So that in both cases you have the same sort of intuition. But also the technical advantage, namely that you will then be sitting with the temporal epistemic logic, and so this is a very studied field, and maybe some results can actually be taken for free from it. So.
I understand your suggestion. My problem with that is that indeed learning by hearing or learning by reflection both has this temporal aspect.
Yes. So my suggestion.
But so then you need some sort of almost interleaving, right, to incorporate them. Well, given that you want to be able simultaneously to say one or the other thing, well, there's some interaction between these two then that is not yet expressed in this logic, I'd say.
Well, for instance, this action that you said is not necessary, as far as I could analyze it while the slide was displayed, it actually was the no learning axiom, and I found it really weird that this axiom should be valid when this is about learning, but maybe so it's probably...
Oh, the cross axiom. Yeah.
So,
No, I think, well, I suppose I think that, well, I'm not sufficiently knowledgeable about the subset space intuitions about this, but I think losing the cross axiom seems to be a real loss. But we had to lose it because otherwise we couldn't achieve the technical result. So it was more but you want to regain this again somehow because it describes a proper intuition. Yeah. Anyway, how much time do I have left? Sorry?
20.
Ah, perfect. So then I have still sufficient time now to wear the other hat. Yeah. Okay, so I continue with Epistemic Logic and Subset Semantics by Yi Wang and Thomas Agutnes. Well, it's true that I present this paper, but I have also been in contact with the authors of this work. So so I appreciate indeed some of the qualities of their approach. In a way, in fact, I think it's fabulous that both these presentations can be presented at the same time, and that the ICLA PC indeed allowed this conclusion. So we can set one result against the other, because I think it would have been very hard to present one paper after the other if the other had already been done. So this is a very nice opportunity for which I want to thank Kamal. Yeah. So here I can, well, part of these slides I can now skip because I've given a similar introduction already. But I now have to point out mainly the differences between the previous presentation that you have already seen. So here, well, the public announcement logic is the public announcement logic as already seen, but the subset space logic is not exactly the subset space logic we have already seen, because it's a subset space logic with what is known here as an epistemic scenario. Indeed, we have, again, structures that are subset models, where we have a certain, domain, where we have a number of subsets of that domain, and we have evaluation of propositional variables. But we don't see here this set of pairs of, point subset combinations. Why is that? Well, that is because in this epistemic scenario, once you have a given, subset O, in the topology, curly O, all X that are element of O, paired with this O are allowable pair subset combinations. In the previous presentation, there was a given set of pairs XO, and not all X in O were allowed, may have been in that parameter set. Here you allow all XO if X is an element of O. So they have, you might say, a more particular setting of subset space logic. Then the semantics of K and box is exactly the same. You know phi in a given perspective X if for all Y that are also in the set O of your perspective, phi is true. And that includes X. Or after any effort, phi if in all U contained in O with the same perspective X, phi is true. Well, not out of my head, but I should take it off now, right? So that should be easy, but I can't do it just like that. Yeah. I'd say the cross axiom is now automatically satisfied, for example, so you don't have to worry about the cross axiom, because if so in that case, the formula that was in the previous presentation, a counterexample, would indeed be invalid here as well. So the cross axiom says that if I have 2 points in a given subset, and I take a larger subset, then those 2 points could also be paired with a larger subset. Here this is trivial, right? But in the previous topology, that was, a requirement. Yeah. Okay, but next issue. How do we do an announcement in subset space logic? And here the solution, find the difference. Now, this is hard, because for me, it's already, an effort to explain to you both these logics and announcement in relation to subset spaces. And now I require you to do this again, but in a slightly different setting. So, for that, my apologies, but let me try to explain the slightly different setting. So the classical public announcement setting would be that after phi psi, if and only if on condition of the truth of phi, the model restriction to the phi states satisfies psi. But then you restrict the domain, and you restrict, you might say, the set of subsets to all subsets that contain phi. Oh, one question to that. When you mentioned that I had 20 minutes, was that based on 45 minutes total for my presentation?
There were some minutes.
Or was it based on 1 hour?
It's based on that 45 minutes, but I thought that 5 minutes more.
Yeah. No, yeah. Thank you. Yeah. So the classical interpretation of public announcement, classical at least, the first intuition on how to do this, we as in Yi and Thomas do not do here. The solution, in a way resembles more protocol logics. Phi may be true, but it may not be allowed. Why may it not be allowed? Well, because the set of phi states, which is a subset of the domain, may not be in the topology. Okay, so that is the restriction. Now, how do the authors here specify that restriction? Well, instead of saying that phi is true, they require that the precondition of phi is satisfied. And based on that restriction, so instead of requiring phi is true, precondition of phi should be satisfied. And the restriction is then, well, only changing the set of subsets, but not the domain. Well, what is my preferred way to explain to you the semantics? Actually, the precondition of phi is phi. That is not so essential. So this could have well have written phi is true. What is essential is that phi should not only be true, but that the agent should be allowed to make phi. That is the meaning of pre-phi in their setting. What does it mean that phi is allowed? Well, phi is, look at the before last item here. Look at the curly phi with respect to the set O. You might call that the interior of the phi interior of the subset O of the subset space. So this one, this curly phi O is the set of points in subset O that satisfy phi. So given a subset O, we look at the O part that satisfies phi. Well, if that set is in the topology, we're okay. If it's not, we're not okay. So the semantics here says that if phi is true, then if this O phi, well, which is this interior part here, if that is an allowed subset in the tautology, then the postcondition psi of this announcement should be satisfied. Otherwise, it doesn't work. And unlike the previous approach, one thing we do not have to worry about is, given that a formula is true in some point, given a point subset combination, if in all the other points that satisfy that formula, those other points in combination with the same subset are in the topology. Here that is automatic because it's epistemic subset space. But we still have the worry that if you look at the set of all phi points, if that complete subset is in the topology. Then that was a worry we didn't have in the other approach. So these are the differences here. Well, then the continuation of this talk is finding out the implications of that definition of public announcement in subset space logic, which is actually a protocol logic-like interpretation of public announcements. You can make the announcement and look at the model restriction as long as that restriction was also a subset allowed in your topology. And then the techniques they use to get axiomatization for that logic are therefore different from the techniques that were employed in the previous approach. And their techniques use, well, what I find an interesting form of embedding of subset space logic into public announcement logic. Why is that an embedding? Because you can see, and then I will talk you through the remainder of these slides, but I'll first give the overall approach here. Why is that? Well, in a way you can view public announcement logic as something inducing a particular subset space logic, namely the logic of all modally definable subsets of a given set. Those are the allowable subsets in your topology. So, and then other subset space logics are, well, similar but have differently allowed subsets. Well, given that, you can therefore use, well, not therefore, but given that it is then possible to use you might say, the completeness proof for public announcement logic, which is a simple reduction argument, well, by adaptation to this subset space logic setting. Because it also applies to the setting wherein not all modally definable subsets are subsets in the topology, but, well, another given set. And therefore I would expect, but this actually I do not know, that therefore the completeness proof here would be somewhat similar to another version of public announcement logic, which you could call protocol announcement logic, where not all true formulas may be announced, but only the true formulas that are somehow allowed. This is a somewhat similar setting. Okay, let me now get you through the remainder of this presentation that presents that axiomatization proof, but I find it, because of the details that then follow, it's somewhat hard to grasp why these details are relevant for this bigger picture in which I view this proof. Given that a formula being true is not exactly the same as the precondition of that formula being satisfied, then you can describe the relations between this precondition on a formula and how this relates to other modalities, both in the logic without announcements and in the logic with announcements. As said, it's pre-phi true is an executability check, given that phi is true, but something else as well. A crucial observation here is that pre-phi in public announcement logic is actually definable as not box phi false or diamond phi true, which suggests actually that you do not use, as the authors have done here, this pre-phi as another primitive in the language, but you could define it by abbreviation in the version of this logic that already has public announcements. But they have chosen not to follow that approach. But given that pre is a primitive, then there's a number of validities you can point out involving pre. I will not go through all of them, but a few. So one of them is that you cannot, announce the false statement. So, or in other ways, you can always announce the true statement, which here corresponds to being the entire domain always an allowable set in the, an allowable subset. Or, for example, that if you have, and here I will just point out a few, if pre-phi is satisfied, then phi is already satisfied. Or that the precondition of phi is also the precondition of the precondition of phi. There are more of these. Concerning expressivity, there is something to be gained from having an additional primitive pre-phi, both in the epistemic logical setting, thank you, and in the setting that also has public announcements. Because pre-phi is not equivalent to phi, but pre-phi means that phi is true and allowed in a setting, you have larger expressivity at the epistemic level, and this transfers to larger expressivity in the level where you add announcements, although the announcements in themselves add no further expressivity to the logical setting. That should suffice as an explanation, and I will shift that part. An interesting point is then that for the completeness proof, the authors want to compare public announcement logic as it is, the Pal K, with public announcement logic interpreted in subset semantics. And here, here again, I can give a more detailed explanation, but I prefer to give the more intuitive explanation that you can see public announcement logic as the particular subset space logic wherein all modally definable subsets are allowed in the topology. Which is essentially saying that any formula that is phi, then the model restriction to phi is an allowed model restriction. So therefore I can replace under these conditions pre-phi with phi. Based on that notion, I can then make, and that comes with defining the topology in this way. Based on that notion, one can then, first axiomatize epistemic logic with an additional pre-phi operator. Well, we keep in mind that this is merely an abbreviation for diamond phi true. And this requires work. Having done this work, then you can put public announcements on top of that logic and have the axiomatization of that logic for free because of these reduction axioms, and which are the standard reduction axioms. But, for public announcement logic interpreted as being over protocols and not over true formulas as such. And well, this is a very schematic winding up of the nice results of these authors. And to mention further research, I didn't talk about a multi-agent setting here for subset space logics, and there are some people having worked in that area, like Heinemann. Well, both Yi and Thomas were interested in these multi-agent settings, and I've been thinking a bit with Philippe and André also about that. Well, I might conclude about what I found a very original idea by Yi Wang on this multi-agent setting, namely that instead of having pairs point subset, in the multi-agent setting you could go, well, actually you could go, to make it work you have to go to pairs point partition, where you might say the point is in the class of the partition, which would previously the point subset in the original subset space logic. So instead of pair subset, where the subset could be an equivalence class for that agent, then you go to pair partition, where the partition includes that particular subset, but now as only one class in the whole partition of the domain. And if you don't do that, you get into terrible difficulties that you want to avoid. But that's for future research, and I will now take off, oops, this hat again, and thank you very much for your attention.
Any questions for the authors to be given to Hans?
Yes, I'm wondering how this logic compares to the constrained public announcement logic of von Bentham, Paquet, Chabrandin, the merging framework for interaction, where they also have a public announcement logic which is constrained by a protocol, and,
yes.
And they also have an axiomatization, which seems to be quite similar to this axiomatization. So, because they don't mention it, so I'm wondering what is the connection.
So I do not know what the precise relation is, but it would be very relevant because indeed the Wang-Agotnas approach uses this announcement as a protocol restricted announcement. So there should be a very clear relation there. Yes, but I don't think that relation is being made explicit in the current paper, at least. Yeah. Okay. But I think you're very correct in observing that this should be found out. Yeah.
Yes.
Okay, mic is right here, so I can grab it. Yeah. So, in fact, I was thinking of this as the answer to Valentin's question, because that entire effort was to start with epistemic temporal logic and try to see how that fits in the dynamic epistemic logic framework. And I see this as a flow of time, but you were, restricting your, right in the beginning, you decide the topology and say how you're going to get the open sets, right? Mm-hmm. Now, I thought one of the motivations for going to this topological framework was to look at richer topologies, right? Like there are intersection spaces, mm-hmm. which are also axiomatized in the same framework and so on. Yes. Now, I don't know whether the idea of announcement can get there, because it's not only restriction to a subset, but to richer topologies, right? I mean, Costas Gargatos has done this work on intersection spaces, and there are probably other works in topologic. So I wonder whether the correspondence can go further, or...
That would be nice, yeah. So I have no idea, but if you could get similar, model restriction, if you get similar dynamic epistemics, say, but on richer structures with more interesting topologies, that is what you suggest, mm-hmm. right? Yeah. Mm-hmm. But I do not know of work already being done in that direction. Yeah.
So another question, related question is also probably, why do you want to have both announcement and subset modality? Because I would have thought that a subset is an abstraction of there is an announcement, right? Which is what seems to be the perspective.
But the funny thing is that Andrei Kurinov wanted it differently, and he could make it work technically. And then I had to give this this sheet in my presentation, trying to wriggle my way out of why this is not one operator, right? But I would prefer to have a logic wherein this is just one operator, and maybe in the future. But partly it was technical convenience that we could make this work. But I know that Yi Wang and Thomas Agotnas are also working in the other direction, where indeed this is only one operator. So I hope they may that they maybe get there, for example, because I think that will be more elegant. Sorry?
It's not a theorem of your system that
No, it's not a theorem that no, and they are indeed different. Yeah, I have to think about it. I'm sorry. Yeah, it's a very obvious question, but out of my head, yeah, offline, please. But yeah, a very good point. Yeah.
Any other quick questions, comments? Okay, let's